Okay, so one of the requests that I had for walking through a proof was this one here in chapter 11 of the textbook. It's this one. You can sort of go into the book and find it. But the idea is that we're going to be proving one of De Morgan's laws, right? The rule that if you have, let me get my little marker going, if you have not P and Q, that is not both, that's terrible. Let's try that again. There we go. If you have not both, you can prove that not one or not the other, right? So what I've done here is I've given a big white rectangle so that we can block off little pieces that we need to block off until we can, see further which way we want to go. So if this is the way you're starting your proof, which is the way you'd start it by writing it down on a piece of paper, you get all your columns, your lines, and all that business, and you put in your given that not P and Q, and what you want to prove is not P or not Q. Okay, and so we know what our goal is. Now notice that you have here a negated conjunction, and there's just no rules that let you deal with that, and so you're just sort of stuck. And so at this point, the first thing to do when you're just kind of not really sure what else to do usually is to go ahead and start a reductio. I mean, that's very often the first thing to do. Sometimes it isn't right, but most of the time that'll get you somewhere. And so in fact, let's see what happens. That is in fact the correct next thing to do. So we're going to assume the negation of the thing that we wanted to prove. Okay. So it's at this point that we, and of course that notice doesn't give you anything more to work with because now you have a negated disjunction, and again, there are no rules for dealing with that. And so you're going to have to make some more assumptions. The question is, what more assumptions? And this is where you want to be sort of thinking kind of ahead. And so again, I'm going to get out my little marker here, and I'm going to change it to a little bit of a thinner line. That should work. Okay. So notice here we have all of this stuff here. Notice this is a disjunction, okay? And so it would be fairly easy if you had not P to get a nice contradiction here with line 2, because if you have not P, you can just use disjunction introduction to add not Q to it. You have to forgive my sort of mouse handwriting, it's not great. And then you'd have a nice contradiction between this and line 2. Likewise, you could get not Q, same story, right? And so the idea is that you'll want to figure out some way of getting a contradiction there. So one way to get not P, right, or to get not Q would be to either assume P or assume Q, right? See what happens. And it's at this point that your thought process can really start to take off a little bit. Because say you end up assuming P somehow. You're like, okay, if I assume P, right, for a reductio, I'm going to have to get a contradiction out of that. Well, now all of a sudden we say, okay, well, P is actually part of this phrase, right? And if I could just get sort of, Q also, I could just put them together and then get a nice little contradiction there, right? And so that means this as well. I mean, I guess I'd have to assume Q as well to do that. And that means I'd need yet one more contradiction, but it looks like we're going to be getting enough of them. Because after you assume both of these, right, you can put them together. And then you have, so we have to count the number of contradictions we get this way. Okay, so once you assume P and assume Q, you can put them together, and then you have a contradiction between that thing here and line 1. Okay, that's one contradiction, and notice we need 3, and so that will end up discharging the most recent assumption you made. That'll discharge this one into not Q. Okay, and because you got not Q, you can then get this thing, which is going to give you a contradiction with line 2. That's the second of the 2 that we need. And then that contradiction will end up discharging the previous assumption you made, which was this assumption P. Okay, that'll discharge into not P, which then, of course, you can turn into that, which will again contradict with line 2. And then you've got that third of the 3 contradictions you need. So now that you've gone through that kind of a thought process, I'm going to have to, we'll clear it and we'll keep going. Then you can really just start going. Okay, and so we knew we wanted to assume P, okay, and all by itself it doesn't do anything, so we wanted to remember assume Q as well. And then the whole point of that was to put them together to get a contradiction with line 1 and start our whole unraveling of all of these reductios. And so when you put them together, you get something that contradicts with line 1. And so that's what you put here on line 6. You just put them together, note that it's a contradiction, and then that will discharge the last assumption you made. That means the assumption on line 4. And then that assumption will discharge, okay, into not Q. Okay, so what you did was you assumed Q, you got a contradiction, and that means, well, not Q then. You know, proper citations and everything like that. Okay, and so now that you have a not Q, you can just sort of add a not P to it using disjunction introduction to get our contradiction with line 2. And that's exactly what we do here on line 8. All right, we just add that little disjunction. So now we get the contradiction that we need to discharge the assumption that we made on line 3, which is what we'll do. We'll combine line 2 and line 8. Note that it's a contradiction, okay? And then discharge assumption that we made on line 3, which was P, that discharges into not P. And now we can sort of do a very similar move that we just did. Since we have not P, we can just use disjunction introduction to create this phrase here again. Okay. And because this line 11 here contradicts with line 2, we have the third and final contradiction we need, right? Which is here. We get it from line 2 and line 11. And then that will discharge the assumption we made on line 2. And that'll discharge into not, it'll just add a negation to the front of it. And of course, that's not all we wanted. So we went ahead and, you know, go ahead and use double negation to drop off these two here. And yeah, there it is. That's how that one works. Right, so for the other one that we had a request about, I wanted to go to, yeah, here we go. So I noticed this is a 11.5, number 6. I had some questions about this one, and I noticed when I looked at my version of the key, I don't know if I updated the one that I uploaded or not or what, but it wasn't on there. So if in case it's not on the one that's online, I'll go ahead and overwrite it. But I thought this was a really good opportunity to show you the process of sort of thinking backward through a proof to figure out how to get one done. And this one involves a decent number of lines and steps, because really it's two proofs that are just sort of glommed together. And you'll see what I mean by that. So the first things first, look at what we have, okay? We're given this information here, not P wedge Q on line 1, and that's one of our givens. And our other given is not Q and not P, which is another sort of a given. And we're meant to prove P biconditional Q. Now, again, you should always think backward through a proof. That's generally the way to do it. And what I'm going to do is I'm going to put some things in here, even though I know we're going to need more lines than this. I'll add them as we go. But we absolutely know at this point that the last line of the proof has to be P biconditional Q. Right? That has to be the last line of the proof, because if it isn't, if that's not on a line yet, then you're not done yet. And if it is, then you're done. Okay, and the justification for that has to be the rule biconditional introduction. We don't know which line numbers we're going to use for that yet, but we know that we're going to end up using the rule biconditional introduction because it's the only way to introduce a biconditional, right? So there we go. And of course, if you look at the biconditional introduction rule, then you know that the biconditional is just a conjunction of two conditionals. The conditional if P then Q, and the conditional if Q then P. Right, we know we're going to have that on some line, and since notice that line there is a conjunction. The only way to get one of those is to introduce a conjunction using the conjunction introduction rule. So we know absolutely that those have to be on the proof at some point. And so now the idea is to get this line here, if P then Q and if Q then P, and then we know that if we can get this one, we can get that one, right? Well, notice in order to do conjunction introduction, you have to have each of the conjuncts on a line of its own. So we're going to have a line with if Q then P, and since that's a conditional, we're going to have to use conditional proof to get it, because that's how you prove conditionals. And you're also going to need if P, then Q, right? And that also you're going to need to have from conditional proof, because it's a conditional, and that's the only way to do that. And so from there, that gives you smaller goals, right? So our ultimate goal is to get here to this biconditional at the bottom there, if P biconditional Q, by way of the conjunction of two conditionals, and then each of those conditionals is going to have to be proved. And so that's why I said this is really two proofs rolled into one. First, we're going to have to prove if P, then Q. Then we're going to have to prove if Q, then P, right? And that's, again, essentially two proofs. But now that we know what we're after, we know how to get started. Okay, so the first thing to do, let's take this this conditional here, if P, then Q, and let us prove it, right? Let us prove if P, then Q. So the first step is then on line 3 to assume the antecedent of that conditional. That's going to be an assumption. We're going to say that's for conditional proof to remind us that what we want is we want the consequent, right? And that's going to be Q. Okay, Q is what we're going to be after there. Okay. So now it's time. Okay, now we have a new intermediate goal. In order to get if P, then Q, right? Now we just need to get Q out of all the stuff that we have. And this is the sort of trickiest step of this particular proof. But notice the work is actually already done for you, because I'm gonna notice what we're doing here. So we're look at that. So that's not P wedge Q, and what we're trying to end up with is if P, then Q. If you scroll up to 14 exercise 11.4, sorry, 11.4, not 14, 11.4.2. Okay, the first proof that we did back then, a couple exercises ago, was we started with not P wedge Q, and then proved if P, then Q, right? And look how we did it. So look, the work on this one's already done. This is a proof we've already done, so it's just going to be part of this new one. The first thing we did was we assumed P for conditional proof, right? And then what we did was we assumed because this here, line 1, is a disjunction, we wanted to use disjunction elimination, which is one great thing you can always do with a disjunction, and we wanted to get Q out of it, so that we could complete our conditional proof. So the idea is, if you assume not P, which is the first part of the disjunction on line 1, then your target eventually will be Q. And then if you can, in order to get Q, you want to assume not Q, do a quick reductio, because you already have your contradiction. You have P and not P already. So just assume Q, or assume not Q, sorry, the opposite of what you want. Put this, the P and the not P together, get your contradiction. It'll discharge into not Q, which you'll drop the negations, and then that's it. So you proved that when you assume not P, you can get to Q. So that's the first half of disjunction elimination. The second half is to assume the other half of the disjunction, which is Q, and all you really need there is then, since assuming Q is pretty easy to derive Q from that, because Q is Q, you can just be done. Okay. And so again, you're going to cite it properly, and then you can complete your conditional proof. So you see how that one works, right? We're going to do the same thing down here. Right, so half of this proof is essentially already done for us. So we're going to need a bunch more lines, as you can see. Okay, and let's do one more of those just for the sake of being fun. Okay. So remember, the first step is then to launch into a disjunction elimination to eliminate the disjunction on line 1 in favor of Q. So we're going to take the first half of that disjunction, which is not P. We're going to prove that when you assume not P, you get Q, and when you assume Q, you get Q. So instead of saying not P or Q, you can just say Q. That's an assumption. That's for disjunction elimination, step 1 of 2. And our target here is Q. And now again, notice that lines 3 and 4 already contradict each other. And so you'll know that if you assume something for reductio, you've already got your work done for you. You've already got a contradiction. So let's just assume the opposite of Q. We're going to assume not Q. That's going to be an assumption for reductio. And now we just want to put together lines 2 and 3. Would be 2, 3 conjunction introduction. Note that it's a contradiction. So far, so good. Because that's a contradiction, we can take the assumption we made on line 5, the assumption for reductio, and say, well, not that. And basically, for RAA, you say, here's the line you made the assumption, that's line 5. Here's the line you got your contradiction, that's line 6. And the rule reductio ad absurdum. Right, and so we wanted Q, not Q. So let's go ahead and just do a double negation to get rid of that double negative there. And so there we go. We've got Q. So we assumed not P, and we got Q. So that means that that first half of our disjunction elimination is done, and we immediately proceed then into the second half of disjunction introduction, which means assuming the second half of the disjunction from line 1, which in this case is Q. So let's mark that that's an assumption. We're going to say why we're assuming it. That's for the disjunction elimination procedure. This is the second of 2 parts of that procedure. And again, our target is Q, but because, you know, Q is our target, we can just stop there. We've got it. Okay. And so now we can just finish the disjunction elimination. We've proven that when you assume not P, you get Q, and when you've assumed Q, you get Q. Right, and so we're just going to eliminate that in favor of Q. All right, so that means that we're going to look at the disjunction that existed on line 1. We're going to point to line 4, where we assumed the left half of the disjunction, and line 8, where we got our target, and then line 9, where we assumed the right half of the disjunction, and also it's line 9 where we got our target. We don't have to write that twice. And the rule disjunction elimination. So that's done. Okay, and so now finally it's time to go down here, and we can start copying and pasting, or rather cutting and pasting. So here, right, we have proven that if P, then Q, because we assumed P on line 3, and then we got Q on line 10, free and clear. So let's just move this stuff up. Okay, and that conditional proof, now we have line numbers to go with it. Okay, those line numbers being line 3, right, where we made our assumption, and line 10, where we got our result. Okay, so that half of the proof is essentially done, right? It's its own little unit. Notice we didn't use anything on line 2 at all, right? And the more seasoned eye, like the more you get practice of this, you'll notice that line 2 just is equivalent, in fact, right, to if Q then P, and so that's why this is going to work. But it's okay, right? You'll be able to proceed fairly straightforwardly with this one. Okay, so we know that the next thing we need to do is start looking at how to prove if Q then P, and we know what the first step has to be. Because it's a conditional, we want to assume the antecedent, and let's keep track of what assumption this is. This is for conditional proof, and we want as a target our consequent. And so we're going to assume Q and then try and get P. All right. Well, it's not obvious how to get there. Okay, there's we can't of course use the P that we have on line 3, because that was an assumption for a conditional proof, and we've already completed that one, right? And so that assumption will have been discharged, so line 3 is not available to us anymore. But the idea is, again, when you sort of run out of ideas about things to do, go ahead and start a reductio. So let's go ahead and assume not P, hoping that we can generate a contradiction and then, thereby sort of get some P. So let's say track that. That's an assumption. That's for RAA. And our target, if once we get a contradiction, we'll get not P, which will be the same thing as P. So at this point, what I want you to notice is this. I want you to notice what we have on line 12 and line 13. We have Q and not P. And notice that line 2 says not Q and not P. Well, if not Q and not P, and we have Q and not P, well, that looks like a contradiction to me. So again, we've sort of already got our work done for us here. We're going to just put together Q and, that's the wrong button, not P. That's just 12 and 13 conjunction introduction, right? If you have any two lines, you can just stick them together with an and. Now notice that line 14 and line 2 contradict one another. So I'm going to make judicious use of the copy and paste tool. On line 15, we're going to say not. Okay. We're going to put together line 2 and line 14 using the rule conjunction introduction. That is also a contradiction. And so then we're going to end up, after I insert a couple more lines, we won't need too many more. That's going to end up discharging the assumption we made on line 13, because that's the last one we made, into not P. So we keep track, that's line 13 where we made the assumption, line 15 where we got the contradiction and the rule reductio. Let's drop those negations off of line 16. And then we can start copying and pasting once again, because notice what we did here. We assumed Q, we proved P. And so that proves if Q, then P. I guess I inserted one too many lines, didn't have to do that. All right, so we're going to take that, move it up. We're going to take this and move it up. And now we just need some line numbers. So it is line 12 where we made our assumption for conditional proof. And it was line 17 where we got the consequent. And so that completes the conditional proof. And now on line 19, we can move this on up. And this here. And now again, we have line numbers to go with it. So on line 11, we proved if P then Q. And on line 18, we proved if Q then P. And so the lines we're putting together are 11 and 18. And on line 20, which will be the last and final line here, we can simply move these on up. And again, we have line numbers to go with this. So this is just line 19. And so when you have a conjunction of conditionals, you can, as long as they're the right conditionals, you can then turn that into the biconditional. That's how you introduce a biconditional. And that's the whole proof. And so you'll notice it was really two proofs. You had to, and most biconditional proofs are this way. The idea is to use a conditional proof going from P to Q, then a conditional proof going from Q to P, and that proves that P if and only if Q. All right. So last thing to do here, and this is something that I guess I wouldn't necessarily encourage, it's a bad habit, but I'm doing it anyway, is that like once we're all done, we can go back and fill in our dependency numerals. This helps you sort of, for lack of a better phrase, proofread the proof to make sure that you're not making sort of a mistake somewhere and doing something a little funny, because if you're doing something a little funny, maybe the dependency numerals aren't going to come out like they're supposed to. But in any case, you should probably fill them in as you go. That's a much better habit than doing it this way, but let's go ahead and fill them in. Because lines 3, 4, and 5 are all assumptions, that's going to be pretty quick. Assumptions depend on themselves. Line 6, right? Our justification for line 6 is lines 2 and 3. That means assumption 2 and assumption 3. Okay. And in fact, because it's a contradiction, that's gonna be the line on which we discharge, right, our assumption on line 5. So go ahead and mark that in. And so on line 7, we have sort of, 5 and 6, but of course, right, 5 gets discharged. So you just end up with what line 6 depended on. Okay. And then because line 8 depended on the same things that line 7 depended on, same thing there. Line 9 is an assumption, so it's going to be dependent on itself. Line 10, this is going to be a fun one. Okay, so we got 1 from line 1. On line 4, we can put that in there. On line 8 here. Okay, yeah, I've goofed this up because this is wrong. Somebody, I'm sure you were all shouting at your screens. Okay, there we go. That's lines 3 and 4, not 2 and 3. That makes a difference. See, proofreading. I did that. That's completely intentional. All right. There we go. Okay, so there we go. 3, 4, and 5 discharges. Now, all right, we have 3 and 4, and because this is the line where we all right, 3 and 4. That's going to be also 3 and 4. And this is the line where we stopped assuming not P, okay, which is the assumption we made on line 4, because we went into the second half of our disjunction elimination. Remember, that's on this line here. Okay, and so that's why 4 is going to discharge here. Okay, so now 4 discharges like it's supposed to. That was the clue for me that something was off, because I shouldn't be adding an assumption at line 4. So 4 is where we made an assumption. We discharged already, so we don't have to have it here. And then line 8, okay, we have 3 and 4, right? And of course 4 discharges. And line 9, right, we have assumption 9, but of course assumption 9 discharges on the same line that it's made, because Q is Q. Okay, so we don't have to worry about that. So we're left with 1 and 3 here for line 10. Okay, because line 3 is we're still dealing with that. And then here, finally 3 will discharge, right? Leaving line 11 to be dependent only on 1, which is just fine. That's one of our givens, and that's exactly what we needed. Okay, so let's continue. Line 12 is an assumption, so it depends on itself. Same with line 13. If we're putting 12 and 13 together, right, that's going to depend on the assumptions made on line 12 and 13. Line 2 depends on itself. Line 14 depends on 12 and 13. Okay. And of course, 13 is going to be discharged here when we get the contradiction. And so line 16 is going to depend only on okay, now 13 gets discharged, so it's 2 and 12, right, from line 15. And same thing here, because 17 relies on the same thing that 16 did. And now here, when we have sort of if Q then P, right, that's where we're going to finish that out. Lines 12 and 17. Okay, so that's going to be 2, and 12 is going to discharge here because we're done with it. And at this point, what we're going to be doing is combining line 11, right? Remember, which depended only on 1 and 3, which discharged, and 18, which depended only on 2 and 12, which discharged. So really, we're just left with 1 and 2. And then same thing here. And so we end up with our final line where we have the thing we wanted to prove. We have shown that the only assumptions we're needing, the only things that line 20 depends on, are our givens at line 1 and line 2. And that means that we are simply finished. If we still had assumptions left over, we'd have to discharge them before we were done. But because all of our assumptions have been discharged to this point, and we're at the place we wanted to be, that's the proof. Okay? So there it is.